Hello, physical science students. This is Mrs. O'Neill. I'm just following up on our start to this new unit with 6.2. We've been talking about energy in general terms, and we also focused in a little bit on temperature versus heat. Today we're going to switch gears and start, the rest of the unit we're going to focus on just one type of energy at a time. So today we're going to focus in on light. Light is something that is around us all the time that we require. We use it in a multitude of different ways, but it's something that maybe we don't understand very well because it's far more complicated than it seems at first glance. We think of light as being like sunshine or light bulbs, but it's actually a lot more and more complex than that. So light is a form of electromagnetic radiation, which means that it's actually made of an electrical field and a magnetic field that are traveling together in the same direction, but they're oscillating in opposite directions. What that means is that, like, for example, the electrical field is going up and down in a wave pattern, and the magnetic field is going side to side in a wave pattern. And they're just traveling together as waves, as fluctuations in the surrounding electrical and magnetic waves, which sounds weird, because how can we see waves? But we do. Light's actually also made of particles as well. The whole thing is very strange. But today we're mostly just going to focus in about talking about it as in terms of what waves are like. So first let's look at what the characteristics of a wave are. We have a wave diagram here. It is one that I'm going to want you guys to be able to label on your notes and quizzes and stuff like that. Not that we're doing like the original tests that I would have had you guys do. Sorry. Okay, so different parts of the wave diagram. So these correspond to the different sections here. So A, the distance that the peak rises or falls below the midline is its amplitude. In sound, amplitude corresponds to brightness and loudness. In light, this is brightness, how bright and shiny it is, how much energy does it have. If it's got really tall peaks, it's got a lot of energy compared to something that's not moving as far, short peaks. The bottom of the waves are called troughs, and the top of the waves are called crests. The distance from one point to the next point, like from crest to crest, or from trough to trough, or even from middle to middle, is the wavelength, and that's going to be important because that helps determine a lot of the different features of it. And then E is just showing which way this wave is moving. It's going in this direction. The notes today are very short. The speed of light. Light is the fastest thing moving in the universe. 3.8 times 10 to the 8th meters per second. This actually equals 3 with 8 zeros, so 1, 2, 3, 4, 5, 6, 7, 8, 300 million meters per second. It is super fast, the fastest thing ever. Nothing can go faster than the speed of light. That's one of the fundamental rules of our universe. It has to do with the way that light and mass and energy distort the space-time continuum and stuff like that. And if you take physics, we'll go into that into a lot more detail, but we're just sort of glossing over it today. So, fastest thing ever, incredibly fast, 300 million meters per second. It still takes the light from our sun almost 8 minutes to reach the Earth. So when we're looking at the sun, we're actually seeing how it looked 8 minutes ago. And when we look out at the stars, we're seeing how they existed hundreds or thousands or millions of years ago. Looking at things is literally looking back through time. But when we're here on Earth, the distances are so short that it's basically real time, that the light travel is instantaneous. Okay, so it turns out that light often behaves like a particle as well. It can be absorbed and released by matter. We call those particles photons. And they're mostly absorbed and released by electrons, which are, part of atoms. And so as we energize electrons, maybe by heating it up, we did this in a lab last fall. We put different chemicals into fire, and then when it changed the color of the fire, what we were doing at the molecular level is we were using the heat of the flames to energize the electrons. They bounced up to a higher, larger sphere, orbital shell, where they'd have a bigger orbit around the nucleus. And then as they lost that energy again, they drifted up to the cooler parts of the flame. The electrons fall back down to a lower shell, and they release photons of light. And the specific frequency or color of that photon depends on which chemicals we're talking about. And that's why we had things like bright pink from the lithium, or copper, which was like a apple green. Or you can get, which one? One of them does pale blue sparks. That one was always my favorite. And I don't remember which one it was. That's going to bother me for a while. But anyway, so you get all these different colors based on the different materials. And the analysis of that colors of the colors of burning stuff can actually tell us a lot about what sort of compounds things are made out of. It's a whole field of setting things on fire just to analyze what it used to be made out of. For real. Of course, we don't usually do like big things, but still. Anyway, so that's actually it for the notes for today. That was really short. Tomorrow we're going to talk more about the different types of light. No, sorry. Next Tuesday, we're going to talk more about the different types of light and the electromagnetic spectrum and sort of the variations that we can see, and maybe learn a little bit of math. We'll see. But for today, we're just doing this. Anyway, hope this helps. Have a great day. Talk to you again soon.